Ladies and gentlemen, we are ready for the SiC presentations from the 6 gentlemen from industry to have discussions afterwards. And we are now starting. I do not want to put more words out. We are happy to be here in reality again, and let's go on. Okay, it's Anup on the list. My kids put you down on the first. Okay, Anup.
Thank you, Bodo. It's good to be here at PCIM. Good to see a lot of old friends, a lot of new people too. I represent Qorvo. We used to be United Silicon Carbide, got acquired by Qorvo. I'm now the chief engineer for power devices at Qorvo. And I want to talk to you about our 750 volt generation 4 surface mount silicon carbide devices. So, all power semiconductor people are constantly evolving their technology, heading towards more perfect, more ideal switches, lower resistance in a given chip size, switching faster, even though the speed is often causing you lots of EMI trouble, but we always constantly try to get faster. And you can see from that chart behind you that in blue is where we've reached on that RDS on versus breakdown voltage plot that device engineers always look at. And the lower you go on that plot, the more ideal your switches are becoming. So those blue dots are showing you where we've reached with our 750 to 2000 volt class of devices. We work on JFET technology because with JFETs, we don't run into gate oxide issues or channel resistance, which allows us to make the chips achieve lower resistances in a given size. So that's what you're seeing there. That's why the blue dots tend to be lower than where the MOSFETs fall or where a GaN device would fall in this RDS on versus breakdown plot. And this is just explaining the reason for why that happens, which is the nature of the oxide interface you get in silicon carbide. So what we build are normally on JFETs. Very few people want to use normally on JFETs. So in order to deliver a normally off device, we use the cascode arrangement. And you can see from the picture behind you, it involves putting a specially designed low voltage MOSFET in series with the device, co-packaging it, so from the outside, you drive it similar to a silicon device. So what we can achieve with that technology, the reason why we do all of this, is ultimately we can deliver very low resistance devices if you do things this way. So lately, I think at APEC, we launched some of our TO leadless package-based 750 volt devices. And you can see that the state-of-the-art device now achieves a resistance as low as 5.4 milliohm at room temperature, 9.2 milliohm at 125C. That package is, I think, 10 by 12 millimeters in size. So it's very useful for certain applications. And the rest of it is just us showing off that it's the lowest resistance device compared to our competition. Now, the JFETs are fairly ideal now, and so the temperature coefficient you see for them is higher than you're used to seeing for silicon carbide MOSFETs because it really represents the intrinsic physics of how the resistance of the voltage blocking layer in silicon carbide changes with temperature. And as MOSFETs evolve and other technologies evolve, pretty much all of us end up on the same kind of curve. So you can see from these curves that the generation 4 type silicon carbide MOSFETs have a somewhat steeper temperature dependence in RDS on, kind of like ours. Just the nature of what is going to happen to silicon carbide devices as they become more ideal. But across the temperature range, what you'll see is JFETs give you an advantage in on resistance for a given chip size. Doesn't matter if it's 25C or 125C. The difference decreases in percentage terms at 175C, but it's always there. And so that's what our portfolio looks like now. You'll notice that this portfolio is largely focused on relatively low RDS on devices. There's not a lot of high RDS on devices. So we tend to focus on where this cascode arrangement and the JFETs will make a difference. So there's a lot of low RDS on examples in there. And you can see that TO leadless portfolio has a couple of parts in blue, which are released, and a couple of parts in red, which are coming soon. And then there's a D-square pack 7-lead portfolio of 750 volt devices, essentially the same RDS-ons, starting from 9 milliohm going to 60. Same devices are available in TO packages, but today I just want to talk about surface mount. So we have just the one type of D-square pack 7-lead package with the high creepage version, so we can put everything from 750 volt devices in there to 1700 volt. All of our JFET die are pretty small, so in order to achieve decent current ratings, we have to sinter the die in the package. So we've been using sintering in these discrete packages for a long time, both in the toll and in this package. And so you can see from the chart, the colorful chart there, we provide the lowest resistance 750 volt device. And even though the die pad and all that is quite small, the thermal resistance number we achieve is good because the chip is made thin and then it's sintered into the package. So once you put it into an IMS type circuit, you can extract a fair amount of power from it. This extremely low 5.4 milliohm device in toll is particularly useful for doing circuit breaker type applications. Again, it achieves a very low thermal resistance because of all the sintering technology, and it's 175C rated. But ultimately, because it's so low in resistance and has a high pulse current capability, you can sustain fault currents in it for a longer time before it blows up. So that is often a necessity in circuit breaker applications where you don't just immediately turn a fault off. You need to make sure it's really a fault. So the devices needs to withstand all of that temperature rise for some time. So these are good for that. And the fact that it's silicon carbide helps because it can get a lot hotter inside before it fails than a silicon device. So I just touched on a few things, but with this wide range of RDS-on classes, very fast switching devices, you can tackle a lot of applications with surface mount assembly instead of traditional through-hole assembly. So onboard charging, off-board charging, D2PAC 7-lead is a popular package for onboard charging. Server power supplies use toll packages quite a lot, so it's good for that. But you can see the list of applications we've listed over there which could benefit from these surface mount FETs and simplified surface mount assembly. It can be just on FR4, doesn't have to be on IMS. Thank you, that's what I have.
So the next on stage.
Test, test. Is it working? No black button. Do I have to push something? It's not sure. Ah, no, okay. So, hello, can you hear me? Loud and clear. Hello, my name is Steffen Ewald. I'm an application engineer at Fuji Electric Europe. And today we will be talking about our 3.3 kV HPNC module. This is the new dual package for traction application. Okay. So, for a long time, it was mandatory for all bits in the traction-related business to calculate the efficiency of the entire vehicle. But so far, in the tenders, this didn't play an important role because the energy cost was not high enough, and therefore it wasn't painful enough for the operators to take this as one, let's say, primary decision to go with one vendor or the other. But now the steeply increasing energy costs make it much more necessary to have a very efficient system. And this is why also in the traction application we see that silicon carbide devices are becoming more and more important. The majority of the losses actually appear in the traction system and in the auxiliary system. But in this presentation we will focus on the benefits for the actual traction system. So the features of this module is we have a laminated internal structure. So the bus bars are completely in parallel, and therefore we have a very low stray inductance in this package. And also it is easy to have the external bus bars in parallel, and then you have a total system with a very good design for low stray inductance. Then this module has round stud terminals at the outside, and this gives the designer of the inverter a lot of space to populate also the backside of the gate driver unit. Then this module also features very well balanced internal gate structure so that all switches which are connected in parallel turn on at the same time and turn off at the same time. Extremely important in silicon carbide devices to have a good balance between the chips. Our module features a magnesium silicon carbide baseplate, and basically most traction modules have an aluminum silicon carbide baseplate. The magnesium silicon carbide baseplate has a lower thermal resistance, but it allows the same delta TC power cycling capability. Then we have a high blocking voltage of 3.3 kV, and of course package compatibility with other suppliers, which is always mandatory. So now we will look at some switching waveforms. On this side we have the turn-on waveform, the turn-off waveform, and the reverse recovery waveform. And what we can see, it's smooth switching, there's not much ringing in the system. And the really interesting part, a bit difficult to read here, these are simulation results comparing the silicon module in the same package. In blue we have the silicon carbide module with our second generation trench MOSFETs, and the green graph is our first generation silicon carbide trench MOSFET. And the reduction here for turn on is 66%, for turn off we are at 80%, and regarding reverse recovery, 98% reduction compared from silicon to a silicon carbide module. So how does it translate into actual use in a traction inverter? So on the left side, we see a parallel connection of two HPNC modules, 3.3 kV, 450 ampere each. Then we have a simulation using our first generation MOSFETs with silicon carbide Schottky barrier diode. The same for our second generation with silicon Schottky barrier diodes. But then same simulation without Schottky diodes. And here, this is a module with increased power. And what we can see here, the best performance for acceleration is the module without silicon carbide Schottky barrier diodes, because we were able to put more active MOSFET area into the device. With silicon carbide Schottky barrier diodes, we were at 750 ampere, and now we could increase to 850 ampere. For regenerative braking, the picture is a little bit different. So here the best performer is actually our second generation device combined with a Schottky barrier diode. Because here the losses, the conduction losses in the diode are lower compared to the version without Schottky barrier diode. But Fuji decided we will go into production with the module without Schottky barrier diode, so the one with the 850 ampere rating. So to summarize this, the 3.3 kV module is equipped with our second generation trench MOSFETs without Schottky barrier diode, and this combines very low loss dissipation with a high power density. And with one module equipped with the silicon carbide chips, we are able to replace two modules in parallel with silicon IGBTs inside. And by leaving out the Schottky barrier diodes, we were able to increase the current rating in this package from 750 ampere to 850 ampere. All right, thank you very much.
Thank you. The next in the row is Ali. Here we go.
Hello, everybody. Thanks, Bodo, for inviting me again. It's been nice to be here again, and as you said, and real, physical. Despite of these noises behind, I guess it's much better to listen to PCIM presentation in a small table in the kitchen. So I guess it's much better missing the people.
This is Infineon's presentation.
Wow, the plan is good. Huh? I'm in Rome, huh? Not Infineon. So it's actually also a promo, this one. It's also interesting, just discussed with some colleagues here, that it's been an interesting time that this dynamic in the last 3 years. So we have to be very careful. The customer went to competitor, competitor went to customer. So I don't know how we have to hold on NDA. So it's now, okay. My name is Ali Mashaly. I'm working for ROHM, not for Infineon. Yes, I'm in charge of the ATSC. ATSC is the Application and Technical Solution Center. In each company, there are some sales guys, but there are some people that should be guilty. and I'm this guy at ROHM. Yeah, my presentation traditionally will not be a one-product presentation. Let's maybe, for the one who doesn't know ROHM, I've just been asked before, ROHM, it's an Italian supplier. No, we are a Japanese company. Our headquarters is located in Kyoto. We are around 23,000 employees worldwide, and I'm coming from Village, which is located close to Düsseldorf. Going forward, one point regarding the most common question during all meetings here about capacity. Yeah. So we have, for the one who doesn't know, that the substrate from ROHM is coming from Nuremberg. It's here, our fab in sea crystal, and we provide this substrate to. We have two fabs. One is Miyazaki, which basically was an IGBT fab. We completely transited to be a silicon carbide fab, and we opened and taken the operation of a new fab last year in Chicago. And our top management just announced yesterday there is a new further investment for the silicon carbide, about 500 billion yen. I don't know if you know the course, so it's more than 3.5 billion euro. Only for the silicon carbide. Going forward, so we have also the back end with, by the way, the laser doesn't work, sorry. So yeah, the packages of discrete devices or even power module. Yeah, so we have commitment to the market. So beside the substrate, the transition is already started from the 6-inch to the 8-inch. And it's the first time from our side that we are working on the same time in next 2 generations. Because we see the tremendous demand in the, not only the capacity, but also in the efficiency increase. So there are 2 different teams, one working for the this 5th generation, and this is here our target to have a further reduction of the specific on resistance, around 30%, and the next one in a further reduction. The chip size is also a big topic at the moment in the market. Today we have the 25 quadrat millimeter. It's already since 2015, but there are some niche segments where we see that a bigger bare die is also needed, and in between the standard will be defined. Next slide is just a complete overview about the lineup, but also the next lineup in our roadmap. Today, if you come to our booth, you're gonna see this package here on the left-hand side. It's very far away from me. This one, this is for application for current rating up to 100 amps. And there is another one here, the DOT247, between 100 and 200 amp. We have the industrial segment to provide it with this C-type package, which coming with the G-type for current rating between 200 amp to 600 amp. And the new package for automotive applications, the molded type, and this is maybe the first time that you see that ROHM is also working on a molded type module for inverter applications. So here in this current rating, we will have 2 versions, one in 400 amp and the other one is a 1600 amp. As you might know, also we have module partners, so providing different solutions, and we are basically open for discuss what kind of package you are asking for, because we cover from bare die up to the module, and this is our target. That's all from my side. Thank you very much.
Thank you, Ali. Now the turn is to Guy Moxey, and we hope we get the right presentation app for him from Wolfspeed.
This is correct. Yes, thank you very much. Ladies and gents, good afternoon. Guy Moxey from Wolfspeed Power. And we're here in this panel to talk about, I think Bodo called it silicon carbide for high voltage applications. So let's just dwell on that term, high voltage. Because if you're speaking with ABB or Danfoss, high voltage to them is 27,000 volts. If you're having a conversation with people from TI, high voltage to them is 30 volts. Jim's there in the audience from GaN Systems. I'm guessing you would class high voltage as 650, 700, in that sort of range. So it's a relative term. So we in Wolfspeed, we are defining what I'm going to talk about here as mid-voltage, which for us is 1.7 kV to 10 kV. So where? And my colleague at Fuji's just shown an excellent application for 3.3 kV for traction. Incredible application. I'm going to dwell on the renewable energy side, which again is another area of mid-voltage, a bastion of IGBT for many years, and can do a lot better. So where? Let's talk about wind power, onshore, offshore, and let's talk about solar. So we're talking utility scale. And I believe, if I remember last year, we did see some 3.3 kV SiC, but it was in TO247, which is a great start, but there are limited applications for a TO247 at 3.3 kV. People want volts and they want amps. They want megawatts. And that's a lot of TO247. So when you look at wind, you're looking at 2 to 6 to 12 megawatts. When you're looking at central utility scale inverters, add in, of course, energy storage, which is another emerging application, we are again talking megawatts. The great news, the fantastic news for simple power engineers like myself, it's a load of half-bridge legs. It does everything you want, whether it's AC to DC, DC to DC if you're charging an energy storage battery, or DC to AC if you're tying back to the grid. Voltage is here, DC coupling. What was yesterday 800 volts, today is 1200 volts. We're now at 1500 volts. So this is where you've got to scale up to that 1.7, 2.3, 3.3 kV, especially when you derate for cosmic radiation, humidity. You need that extra safety headroom that silicon carbide now is bringing to the party in a modular form. Let's take some examples. Let's look at some products. You've seen a 3.3 from Fuji. Excellent, 850 amps. We're showcasing a 3.3, 800 amps. 1.7, 2000 amps. And 2.3 kV at 1500 amps. So I'm going to stand here and use the phrase, one person is lonely, two people are company, and now there's two people with 3.3 kV in true power. But the important thing is here, is think of an IGBT, that's the baseline system. It's working its hardest at 800 hertz to 1000 hertz, 1 kilohertz, it's switching capable. When you migrate to silicon carbide, you're not turning a motor. In a solar application, for example, it's a static power conversion. If you're charging a megawatt battery, you can increase that switching frequency. There's no dV by dt isolation challenges of motor windings. If you're using an IGBT, you've got to derate massively as you increase that switching frequency. We're operating 1.7, 2.3, and 3.3 kV at megawatt levels at 8 to 10 kilohertz. So this is magnitudes different from where you are limited with an IGBT. You can see here at 10 kilohertz, we're 800 amps on the 3.3 kV module, as per the datasheet. Your IGBT module at 10 kilohertz derates down to 200 amps. So you now have that flexibility to increase the switching frequency. And let's see the impact this brings. Why are we so excited about increasing switching frequency? This is a 1 megawatt transformer at 10 kilohertz. 1 megawatt. If this was a silicon-based system tied to the grid, that transformer would be the size of a small car. So this is the impact of increasing switching frequency, which the silicon carbide power module brings. This example here is a PV system directly connected to the grid at 8 kV. 8 kV directly switch mode connected to the grid. This is the impact of mid-voltage silicon carbide that's available today. And when you look at a scale, you've got to have the products. If we stick around the renewable spectrum, ranging from 5 kilowatts in the residential system, around the discretes at lower voltage, moving up into the string systems at 20, 30, 40, 60 kilowatt with the Wolfpack modules, jumping into hundreds of kilowatts with the XM3s and the BM3s. And now we really can truly take you up to the megawatt scale with our new mid-voltage product. Thank you very much.
Thank you, Guy. It's Eugen. It's your turn. It's the Mitsubishi
1, 2, 3.
presentation. We got the right presentation. Thank you.
Good afternoon, ladies and gentlemen. Next couple of minutes with me, with Eugen Stumpf, with Mitsubishi Electric, and first of all, thank you to Bodo, thank you to Mr. Mashaly to have a possibility to talk to you, to this great audience. My topic is today to talk about different, different aspect of silicon carbide, not about performance, because we talk since decades about performance, and I actually personally, I am tired to hear about performance. We understood everybody that silicon carbide perform better. I would like to talk about a little bit about packaging, a little bit about reliability. What is silicon carbide? For sure, silicon carbide is a sun. Yeah, sun providing us a possibility to live in the greener tomorrow, to live in the sustainable future. But how to use this sunshine? We see today a lot of market requirements and system benefits. Market requirements are performance, high efficiency, what I will not touch today or will not touch directly. Standard package is a must because second source, we have low internal inductance requirement, we have high switching speed requirement, and we have high stability in lifetime. Then my question, do you discover contradiction here? Personally, I see contradiction in standard package and low internal inductance because today standard package, not all package provided low internal inductance and means alone not having a higher switching frequency or a higher switching speed. Let's take a look on packaging, about what we're talking today. What is a market standard package? First of all, LV100. LV100 was developed for using silicon carbide. And we see today already a great presentation from Fuji Electric and from Wolfspeed. We have 62 millimeter package. Feedback from the market, good enough for silicon carbide. Okay, let's go with this. But who is Akunin? Who is Sorgenkind here? It is for sure a NX package what is not prepared for silicon carbide, what have a quite big internal inductance. How to proceed here is presented on the next slide. Actually, the conventional package of NX, and what Mitsubishi did, we provided laminated busbar inside to the module. Means DC, plus and minus, go inside into the module and allow to compensate magnetic flux. Result is 9 nanohenry between P and N. Original package 17. Means we approximately half of this inductance, and now we are ready for silicon carbide. Results are here. Without touching of chip performance, we reduce switching energy by half just by introduction of a new packaging technology, and we respect safe operating area and reduce and switching energy. Result is here. This is silicon carbide, non-compensated or traditional package. We see here 75% approximately, and that just by introduction of your new package, we see higher efficiency, means 85 lower losses. Result of this investigation is now under discussion in the lobby of PCIM. This is a poster session presented by Mr. Goto and managed by chairperson Cristiana De Marino, chairlady. What is the next contradiction here? It is for sure high switching speed or higher stress by electrical field and high stability in lifetime, what is also expectation. How to handle here? I would like to distinguish here between DC stress and AC stress, steady state stress and dynamic stress. This is reliability result of Mitsubishi. First of all, Hall test, high acceleration test. In our life, we should handle 5 megawatt per centimeter, and this is our test result, and we will see approximately 10 times 7 years in operation without sacrificing of our lifetime. This axis is in second, but I think we are humans better to count in years. It's 10 times 7 years. If we will make a stress by plus 20 volt, minus 20 volt, with highest specified temperature, 150 degrees C, we see no deviation of threshold voltage. Yeah? Threshold voltage is stable. We're talking about 1,000 hour testing period. Let's change to the AC stress or dynamic stress. Fact today, actually this is a reference as a JEDEC. Fact today is what the switching frequency with number of increasing of number switching frequency, threshold voltage will increase. Problem? Maybe no problem, because if we will take a look on the result of Mitsubishi Electric result, we're talking here. Actually, this is a cycling or number of cycling. This is a threshold voltage shift. If we will start here, and here's an automotive board according to JEDEC, and this is a board for renewable energy for 20 years lifetime, operating 12 hours per day. We see shift of approximately 0.3 volt within 20 years, and for automotive shift is below of 0.1 volt. Academia talking about 2 volt or even 3 volt shift within 20 years, but the real data shows just a 0.3 volt. And here's how to say, the message is here, please sleep well, yeah? Within next 20 years, threshold voltage will increase not so significant, within 1 volt or within 0.5 volt. If you would like to talk about next contradictions where in this hall, just have a direct line from this podium stage directly to Mitsubishi Electric. I will be here. Once again, my name is Eugen Stumpf, and back to Bodo.
Thank you, Eugen. Now, I want to say now we got the Infineon presentation. It's Vishal doing it.
So good afternoon, everyone. My name is Vishal Jadhav. I'm the lead principal focusing on high voltage silicon carbide. And my today's topic would be focusing on the 3.3 kV CoolMOS. And here I would like to focus more on the technology aspects, its features, and then would like to give some insights about the impact of this silicon carbide on the high power application. Let's start a bit with the history and the experience. So at Infineon, we have close to more than 20 years of field experience in silicon carbide. And where the journey goes is, if you look at the screen, we started well way in 1992 with the first development of the silicon material or the silicon transistors. And the next highlight, which was clearly seen from this particular journey with silicon carbide, was in 2016 when we did a technology launch of silicon carbide MOSFET, more in the range of 1.2 kilovolts. The next years, we defined different kind of packages, starting from the easy package and the discrete package, which houses this CoolMOS silicon carbide. And then we progress further in the journey by introducing more package with silicon carbide. The journey continues further. So this PCIM, what we bring, is the first 3.3 kV silicon carbide MOSFET module in XHP2 housing with 1,000 amperes of nominal current and with the combination of our most robust .xt technology. The most important question always is why the trend structure? So of course, clearly from the trend structure, we clearly see the advantage of the aligned channel plane, where we have a very good channel mobility and also a very low defect density. And this combination of having a lower RDS(on) times A, the higher threshold voltage, and most importantly, to have a much more robustness in terms of manufacturing, allows us to have a very good balance to design with the trench MOSFET. What we clearly see as an advantage what the trench MOSFET clearly brings is, of course, a very low RDS(on) times A. We also see a very great reliability in terms of the gate oxide, which is critical for everyone for the application where you focus on reliability. And then to ensure to have a higher VTH, which avoids any parasitic turn-on. The other most important is that we clearly see a potential to further shrink the cell structure to gain more benefit with the next generation. And of course, the trench was clearly of years of experience from the IGBT industries to the silicon carbide, where we have enormous experience in this particular technology and gate structure. What I would like to focus is also a part of our publication is, of course, we took the existing optimized 1.2 kV silicon carbide MOSFET, but we clearly see that this is not enough to go to, or it needs to optimization to go to the higher voltage. Clearly, the impact is clearly in the JFET structure, where we see definitely we want to optimize the JFET doping and the geometry, and to adapt it to high voltage, where we will be able to have the same gate oxide field strength. And what we clearly see in this particular graph is that we have a higher RDS(on) if we have ended up with the same JFET structure. What you could clearly see is that the contribution of the JFET, which basically means that we will have more JFET resistance in the structure, would mean that we would end up with a higher RDS(on) if we would have ended up with the same JFET structure. And what we did with the optimization, the implant, is to have a high voltage trench MOS, where we are able to really bring down the JFET, losses in the JFET, almost close to a planar MOSFET. And this was considered to be the base for our next 3.3 kV silicon carbide MOSFET. What you see is, of course, many can make a very good chip, but every chip needs a package, and it's very important to really house this package. One of the challenges with the silicon carbide MOSFETs are, of course, these are very small in size. And as it's a very smaller in sizes, you have to dissipate a large amount of heat over a very small area. And when you now focus on applications like traction, which most of my colleagues also mentioned here, it has a very high cycling requirement in terms of load, which means at the end, you have a very smaller chip, which has a very low or higher RTH value. At the same time, it needs to fulfill the traction requirements or fulfill the cycling capability. What we clearly see is, in order to really bring the combination of this very good silicon carbide MOSFET chip, is to combine it with a very low inductive package. And here we introduce the silicon carbide MOSFET in an XHP housing, which has a strain inductance less than 10 nanohenry. What it brings, of course, is in combination that we not only rely on just the chip, but also to introduce the .xt technology. With .xt, what you clearly see is that the silicon carbide chip is sintered to the substrate, and on top we have the copper metallization and the copper bond wire. The clear advantage what it brings is a very high power cycling capability, but on the same other side, as we have an inbuilt body, or we have the body diode, it also increases the surge current carrying capability of the module. And this, for applications like traction, where you need a very high surge current capability, is one of the main advantages which the .xt technology brings to the module. The next, I would like to focus with the combination. So what this combination of low inductive design of fast chips bring. So the 3.3 kV MOSFET, what we are introducing into at PCIM this year, is designed for very fast switching and low losses. We are talking about here with a switching turn-on speed of around 7 kiloamperes per microsecond, and the turn-off speed of almost 17.5 kV, dB parity of 17.5 kV per microsecond. And what you clearly see is that because we have a low inductive housing, the turn-on high switching transients is almost negligible or very low compared to if the design is put into a high inductive module. And the same is on the turn-on behavior. We see from the temperature absolutely no dependency on the turn-off losses. This is in the range of around 450 millijoules for 1000 amperes. And when we go in the terms of turn-on, we are in the range of around 180 millijoules for the turn-off, and around 450 millijoules for the turn-on energy. Of course, at higher temperature, there is a slight plasma built up in the body diode, because of which there is a higher ion losses at higher temperature. The next aspect is what I'm talking about is the benefit of cool-SiC interaction. What we clearly see is the energy saving is clearly one of the advantages which silicon carbide brings. If you now compare the traction application, you have a traction application with the 4-quadrant converter and the inverter. These are the two main components of the traction. And if you now take a silicon carbide-based converter at 100% of its power, the silicon carbide reduces this power consumption almost by 10% of energy saving. And this 10% of energy saving is almost coming out of the transformer and the 4QS optimization. And the other 4% comes from the other component in terms of the motor and the pulse inverter. What it clearly brings from the overall, a 10% lower losses in the transformer and the motor results, a volume reduction by 20% because of the smaller size of the systems, and also a reduced cooling effort because at the moment you see silicon carbide have a very low losses, which means the cooling can be optimized to really have this lower or these housings. And then when you are operating at higher frequency, there is a benefit of reducing the losses and thereby also reducing the fan in the system. So you can go from actually forced air-cooled system to a motion air-cooled system just by having a lower losses of silicon carbide. With this, I'm at the end of my presentation where we would like to summarize that the high voltage silicon carbide MOSFET structure gives us an advantage in terms of the gate oxide reliability, the RES on times A, and the threshold voltage. The second aspect is by combination of silicon carbide in the low inductive XHP housing and .XC technology makes a good combination of silicon carbide with lower losses and a higher cycling capability. And what it brings at the end is that for the traction application, the energy saving is in the range of around 10%. There is another benefit in terms of noise reduction, cooling effort, and enables the compact design. For more information, we would like to visit us at our booth. And we have 4 publications on the 3.3 kV, starting on the chip technology, focusing on the module, then going into the module and the application, and the demonstrator which shows how a complete low inductive system can be designed. Thanks for your attention, and if you have questions, then we are ready for it. Thank you.
Thank you, gentlemen.